This conference will now be recorded.
So very good evening, students. Today we'll be discussing the remaining part of the viscosity, which we had already started. Viscosity of fluid. So that part will finish today. And if time permits, we'll take a few numerical problems in today's class. So before I start today's class, I'll just briefly summarize what we had already done. We had already learned what is viscosity. Viscosity is just a frictional force among the layers of the fluid, okay, between the layers of the fluid. So if the fluid is moving in this way, v, this is v plus delta v dv, so viscous force will act in this way, so it will try to oppose the relative motion as it does in case of, as resistive force does in case of solid, like in the solid surfaces, okay. The same thing when we see between the layers of fluid, that is named as viscosity, okay, that is viscosity. We have already learned what is viscosity and how it arises, etc. We have learned. Now we'll start from here. We'll see how viscosity, coefficient of viscosity, changes with temperature and pressure, or in other words, what is the effect of temperature on viscosity. Look, when liquid is heated, the kinetic energy of its molecules increases and the intermolecular attraction becomes weaker, okay. When we increase the temperature or heat a liquid or fluid, any fluid, the, the intermolecular force become weaker and that their kinetic energy becomes more, and because of that viscosity of liquid decreases, or in case of liquid, if we increase the temperature for a liquid, okay, let us say effect of temperature on viscosity. So for liquid eta, coefficient of viscosity decreases as temperature increases, as T increases, okay. Why? Because intermolecular force become weaker as the kinetic energy of the molecules increases, okay. And there is an empirical formula, you may remember this, with temperature. So eta t means the coefficient of viscosity at any temperature T. This is at 0 Kelvin, sorry, 0 degree centigrade. Eta 0 is at 0 degree centigrade, divided by 1 plus alpha into T plus beta T square, okay, where this alpha beta are arbitrary constants, okay, and T is temperature. So this is an arbitrary arbitrary empirical formula, and this formula was given by Slotels. Empirical formula. Okay, empirical formula. Now we'll see what happens upon like if we increase the temperature in case of gas. So in case of gas, what will happen? The See, in case of gas, how viscosity occurs? It is due to diffusion. Due to diffusion. Okay, viscosity occurs due to diffusion. Diffusion means gas molecules of greater density will diffuse towards the lesser density part. Okay, that is diffusion, and because of diffusion there will be viscosity. And if you increase the temperature, the diffusion of molecules from one moving layer to another moving layer will be increasing actually. Okay, it will be increasing, and it has, see, diffusion is directly proportional to the temperature T. Diffusion is directly proportional to this. Therefore, we can say the viscosity also increases, but it it is proportional to square root of T. This is for this is for gas. Okay, viscosity, how viscosity changes with temperature. This is for a gas. Now, effect of pressure. How pressure can affect? Effect of pressure. So, except water, viscosity of liquid increases with increasing temperature. Except water, viscosity increases for other liquids as the temperature increases. Okay, I'll tell you effect of gas. Sorry, effect of pressure. Effect of pressure. Effect of pressure on viscosity. For a liquid, viscosity will increase upon increasing pressure. As you know, you will have greater intermolecular forces, etc. In case of water, viscosity decreases with increasing pressure. Only in case of water. For water, it decreases up to certain pressure. But for all other liquids, eta increases upon increasing pressure. Okay. And what about the viscosity of gas? If we increase the pressure, actually it is independent of pressure. So viscosity of gas. So this is one point. This is second point. Viscosity. Viscosity of gas is independent of pressure. You have to remember this point. Independent of pressure. Okay, independent of pressure. So all right, with this part is over. Now we are going to learn few very interesting and very important topics. Those are Poiseuille's formula. Then we'll learn about Stokes law, terminal velocity, etc. So what is Poiseuille's formula? What does it state about? Actually, it is concerned with the flow rate of liquid or fluid through a capillary tube. It is the flow rate. So the volume of the liquid flowing out per second through a capillary tube of length L, radius small r, under pressure difference applied, say under pressure difference P, applied across its ends. Suppose I have a capillary tube like this. If pressure difference across these two ends is P and it has length L and radius small r, then the volume of the liquid or fluid, any fluid flowing out per unit time. So suppose that is the volume is the Q, which is flowing out flowing out in t seconds, suppose, then we can write the flow rate. Okay, so this is suppose Q is the volume flowing out per unit second or per second, flowing per second, okay, through this capillary tube which has length L and radius R, and that can be given by Q is equal to, see I'll write here, font is smaller here, so Q is equal to pi, P is the pressure, R to the power 4, that is the radius to the power 4, 8 eta and L. What is eta? Eta is the coefficient of viscosity. What is P? P is the pressure difference maintained across the ends of the capillary tube. What is L? L is the length of the capillary tube. What is smaller? Smaller is the radius of the capillary tube. Okay, so this is an empirical formula, because empirical in the sense, see, when we see some experiment, when you do some experiment, we get some result. Okay, we get some result, then actually in science, if you get some result, that is not all in all. You have to interpret the result also. What does it signify physically? So when you get some result out of experiment, you have to interpret it. So to interpret any result, experimental result, sometime we give some logical explanation. That is actually sometimes some logical formula, sometimes some logical definition. Those things are actually empirical. Empirical in the sense, they don't have, empirical formula don't have a strong theoretical basis. So those are called empirical formulas. Okay, so this is kind of an empirical formula. So how do you derive this empirical formula? This empirical formula is actually derived from some concept along with dimension analysis. So we'll derive this Poiseuille's formula. Here we have got Poiseuille's formula as pi p r to the power 4 by 8 eta L. So how do we get this formula? We'll derive out of dimension analysis. Okay, from dimension analysis. Let us see what are the assumptions. Poiseuille. Okay, so this formula is called Poiseuille's formula, and to derive this Poiseuille's formula, there are certain assumptions. Okay, what are the assumptions? First assumption is that the flow of liquid is steady and parallel to the axis of the tube. So I had drawn this tube, right? Sorry. So first of all, the flow of the fluid has to be steady flow. Sorry, this is steady flow. That means there will be no vertex or random flow. There will be steady flow. That means per unit time, the flow out of the liquid or the fluid will be the same always. So that is actually steady flow. So first assumption is flow of the fluid has to be steady and parallel to the axis of the tube. Of the tube. First assumption. Second assumption, there are few assumptions. We'll write all those. So the pressure is constant over any cross section of the tube. So pressure has to be constant. So pressure difference is there. So but that pressure difference has to be constant. Pressure is constant over any cross section. That means if we just take this place, this place, or two ends, everywhere the pressure difference has to be the same over the over any cross section. Okay, any cross section. Now liquid velocity is zero at walls. So this we have already learned from viscosity also. The the velocity of the liquid, see the third point, we had already discussed this in viscosity. Velocity of liquid, here I'm just taking as liquid, velocity of the, sorry, let me take it fluid itself. Fluid. Velocity of the fluid in contact to the capillary wall. Capillary wall is zero. Okay, this we had already discussed. Suppose this one was the capillary, this very layer which is in contact with the wall of the tube. So that is at rest. That means that doesn't have any velocity. Now fourth one is the tube is horizontal so that there is no influence of gravity. Tube has to be horizontal, is horizontal, gentle, so no effect of G, no effect of G. Okay, in the horizontal line everywhere G is same, but if we go vertically G may vary, but within the limit of like lower distance from the center of the earth, lower height, in a sense I'll just, so if the height is, if the height is much less than the radius of the earth, then everywhere G will be same as G in the vertical direction also, but horizontal direction everywhere there is G. Okay, so that there is no effect of G. That's why there will be no effect, no change will happen by the G. Okay, these are the assumptions in Poiseuille's formula. Now we'll derive the Poiseuille's formula, and there we'll see how any empirical formula can be derived by using dimensional analysis. So I'll just recap these four assumptions. Flow of the fluid has to be steady and parallel to the axis of the tube. Then pressure at any cross section has to be same. Then velocity of the fluid in contact has to be zero, and tube has to be horizontal so that no effect of G will be there. So these are the assumptions. We'll remove this. Now we'll derive the formula. Okay. To derive Poiseuille's formula, what Poiseuille thought is that the fluid flowing out per second through a capillary tube depends on the coefficient of viscosity. So Q is proportional to some proportionality. We don't know what it is. So that's why he had taken eta to the power A. Then it is it depends on the flow depends on the tube of the radius also. Rate of flow, sorry, radius of the tube also. Let us take, we don't know how it varies with the radius of the tube. Okay, while we are deriving, we write eta to the power A and B are actually then some numbers which we will get after dimension analysis, and R to the power V, and it depends on the pressure gradient, that means pressure per unit length. Pressure gradient, this is called pressure gradient. Okay, this is called pressure gradient. All right, so we'll write that also. P by L, this is a pressure gradient, whole to the power C, suppose. Okay, whole to the power C. Now you have to do the dimension analysis to find out the value of A, B, C such that you get a relationship between, see, this Q is actually V by T, that is the volume per time. Okay, this is Q. So if I do the dimension analysis, so Q from here, so Q, dimension of Q will be equal to, sorry, yes, let me write in terms of equation. So K is dimensionless constant. Suppose dimensionless constant, you have already learnt in 11th standard, so that knowledge will come in use here. So dimensionless, K is a constant, dimensionless constant, because there is a proportionality over here. I am just making it an equation. So you have to bring a proportionality constant. This is dimensionless constant. Now eta, dimension to the power A, dimension of R to the power B, dimension of P by L to the power C. Okay, now look what we have to do. We have to, okay, so we'll get it here. Q is equal to K eta whole power A, then R whole power B, then P by L whole power C. Okay, now dimension of eta is what? Dimension of eta is m L to the power minus 1 T to the power minus 1, that we had already derived in the last class. Okay, and see, R is a radius, so it has just length to the power B, and pressure will find out pressure gradient. See, pressure is m, this is actually force per unit area, so area means L square, and force is mL to the power minus 2, mL to the power minus 2 divided by L square, so you'll get mL to the power minus 1 T to the power minus 2. This is the pressure gradient. Oh, obviously there is another L over here in the down, so it will be this will be m l to the power minus 2, and here whole to the power c. Okay, whole to the power c. If we want to write c, then yes. So now look, I'll write in the left hand side. What is that? Volume is L cube per t. So L to the power 3, t to the power minus 1. So this is the left hand side. Okay, I'm writing this equation itself. Now k is dimensionless constant, and you have eta. See, eta to the power a. That means m to the power a, l to the power minus a, t to the power minus a. Okay, into here L to the power b, then you get this one, m to the power c, L to the power minus 2c, t to the power minus 2c. So these are the things we get. Now look, what we'll do, we'll MLT will just separate them out. A, C, L, M is here, A plus C. Okay, then we write L. For L, what we get? This is plus A minus A plus B and minus 2C. So we have to write minus A plus B and minus 2C. Now what about T? That is minus A minus 2C. Okay, now you look here, left hand side and right hand side, if we just equate the coefficient, yes, the power of m, if we compare with here, so there is no m, so power of m will be, see here I can write m to the power 0. So a plus c is equal to 0. We can write it, a plus c is equal to 0. So here we can write a plus c is equal to 0, one equation. Then from here L is equal to 3. So this minus a plus b minus 2c is equal to 3. Sorry, minus a plus b minus 2c, that is equal to 3. So this is another equation, say. And with t has minus a minus 2c is equal to minus 1. Minus a minus 2c is equal to minus 1. This is equation 3. Now see, from any one, if you suppose this a minus 2c is equal to minus 1. So from this two we can get uh, b minus 1 is equal to 3. So you get b is equal to 4. Okay, b is equal to 4 from this equation 2 and 3. So once we get b, let me check from here. If we put the b, then we'll get a relationship between a and c. From equation 2, b is 4, so minus a minus 2c is equal to minus 1. We can write that because b is 4 plus 4, it will go in the right hand side as a minus. So we can write that a plus 2c is equal to 1. Okay, okay, so this we had already, but now a is equal to minus c. So let us write a is equal to minus c. So let us write a is equal to minus c from equation 1. So you have 2c is equal to 1, so c is equal to 1. If c is equal to 1, c is equal to 1, c is equal to minus a, c is equal to minus a, so a will be minus 1. If c is equal to 1, a will be minus 1. So let us see what we had start with. We had start with this b to the power this eta to the power a. A means how much we have got? A means minus 1. Okay, so minus 1. So q, see, k is equal to eta to the power minus 1 means eta comes down. Then b, see, r to the power b. R to the power b means b is 4. So you get r to the power 4 up. Now, yes, so a is equal to minus 1 and c is equal to 1. Sorry. We had written here. So p by L is equal to c. P by L is equal to c. So c is 1. Sorry, p by L whole to the power c. C is 1. So what we can write is here. So we can write p by L. So we have got r to the power 4 p by eta into L. So this part is already got obtained. So p r to the power 4 by eta into L. Now this value of k is found to be this much, pi by 8 L. Sorry, 8 pi by 8. So if we replace this value of k with pi by 8, then what we get? Pi with r to the power 4 p divided by pi by 8. So 8 eta L. So this is how Poiseuille's formula is derived. Okay, this is an empirical formula, and this formula can be derived from dimension analysis only. Okay, so here k is having a value. K is having a value pi by 8, and if we put that, we get the equation what we have written over here. Okay, this is Poiseuille's formula, and how to derive Poiseuille's formula I have taught you. Now we'll go to Stokes law. Okay, or viscous drag on falling body. Viscous drag on falling body. Okay, so it is from our practical experience. You might have seen, if you drop any object on the top surface of the liquid, and then when it moves with certain velocity within the liquid, you will see that the motion of that particular object within the liquid is actually slowing down or retarding. Okay, look here, if we take a ball or anything, any object having certain density rho, and we have taken certain fluid, certain liquid having viscosity eta and density sigma for the liquid. Now you are just dropping the ball such that it falls through the liquid with certain velocity. So what will happen? What are the forces will act on this ball, and how will be the velocity, etc. we'll be discussing here. And that is actually, though all those details were given by Stokes, so we'll learn what is Stokes law. First of all, we have to understand how the viscosity, because the fluid is actually not moving. We have seen that viscosity arising viscosity arises when there is relative motion between the layers. There is a relative motion between the layers. then viscosity arises. Okay, but in this case, you look, if you have a beaker or some container which has a particular liquid having density sigma and it has coefficient of viscosity eta. How this viscosity is arising if this is at rest? At rest, the fluid is at rest, no motion. But how do you get the effect of viscosity on this ball? Look what happens. As such, there is no relative motion, so no viscosity. But when the ball is just falling through it, the fluid or the liquid layer attached to the ball will move with the velocity of the ball. Okay, let me repeat that. The layer of the fluid or layer of the liquid in contact with the ball will move with the velocity of the ball itself, and rest of the water will be at rest. Like if the ball is here, the layer attached to this will be in motion, but this layer is actually not in motion, it is at rest. So therefore it both of them have a relative velocity. Someone has greater velocity or no velocity, and someone has velocity. Therefore there is a relative velocity between the layers, and hence viscosity comes into play. And how does this viscosity comes into play? See, it is, see, the ball is moving in this way, so fluid is moving in this way. So the viscous drag will be acting opposite to the motion of the ball. Okay, so viscous force will act in the opposite direction, in the opposite direction of the motion of the ball. Suppose the ball is moving downwards, so viscous force will be in the upward direction to oppose the relative motion. Okay, so this is how viscous drag arises when a body is falling through a fluid. Okay, now Stokes has given nice empirical formula. What is the viscous force, magnitude of the viscous force acting on this ball? If you know the radius of the ball, if you know the velocity of the ball, if you know the coefficient of viscosity of the fluid, then what is the magnitude of the viscous force on such ball which is flowing through a fluid? So that's where comes Stokes law. Stokes has given that formula, okay, or that law. So according to Stokes law, according to Stokes law, the backward viscous drag or opposing viscous drag we can write, or let us write backward viscous drag, viscous drag, viscous drag acting on a small spherical, acting on a small spherical. See, we are just considering the object to be spherical. Spherical body of radius capital small r, of radius moving with uniform velocity v, uniform velocity v is given by f is equal to 6 pi eta r and v. R is the radius of the spherical ball, eta is the coefficient of viscosity of the liquid, v is the speed of the ball or the velocity of the ball through the fluid, and this is the constant, proportionality constant, 6 pi. Okay, so this is actually Stokes law. Now we'll be deriving Stokes law. This is also a kind of empirical formula. We'll derive this Stokes law by using dimensional analysis again. So you have to remember, before you go for dimensional analysis, you should have some prior idea that the viscous force may be depending on which parameters. So that idea you should have before you go for dimension analysis. So not only in this case, for any case when you go for dimension analysis to find out a relationship or any formula, for that case at least you should remember the parameter. You should at least know the parameters on which a particular force or equation like or any parameter depends on. That means I want you should remember, you should have some prior idea about the parameters. Okay, parameters on which here the viscosity or viscous force depends on coefficient of viscosity, radius of the sphere, and the speed of the sphere. That's why we have, okay, so 6 pi eta rp. Anyway, now we'll try to derive this formula. I'll just show you. You can do it as a homework. See, similar way will be deriving. Similar way will be deriving. See, we know that the force viscous drag may be proportional to eta, but we don't know up to what power. So A, let us write. It depends on the radius of the ball or the sphere. So let us write B, and it depends on the speed C. Now this has dimension of force. This, you know, the dimensions of this, all this. See, I'll just quickly do it. So ml t to the power minus 2 in the left hand side, this has dimension of force only. On the right hand side, eta is m l to the power minus 1 t to the power minus 1 whole to the power a. R is l to the power b, and b is l t to the power minus 1 whole to the power c. Now if you take the powers of m, l and t from both sides and equate them, you will see that a b c, a equal to b equal to c will be 1. So that's why, see, and proportionality constant is 6 pi. That's why you get 6 pi eta rv. So this is the Stokes law, and this is how you have to derive. Now you have to remember that there are certain limitations where you can use Stokes law. First one is the fluid through which the body moves has infinite extension. The second is the body is perfectly rigid and smooth. So in that case, the Poisseuille's law will be, sorry, Stokes law will be valid. There is no slip between the the ball or the sphere and the liquid, or sorry, or the fluid, and there will see the there will be no turbulent motion or eddies. Okay, that means streamline motion has to be there, and size of the object is small but it is larger. See, size of the ball which was flowing through has to be small, but the dimension of that ball has to be greater than the dimension of uh, yes, so the ball here look okay, so that has to be, sphere has to be small enough, but in greater than interatomic separation. Okay, that's why this sphere will see uniform uniform or homogeneous medium or continuous medium and for such a body. Okay, anyway, so these are the assumptions, sorry, limitations where we can only use Stokes law. Now we'll be learning the most important part, that is the terminal velocity. So what is terminal velocity? See, look, when a, a ball suppose has density rho, it is just falling down through a viscous liquid or viscous fluid which has density sigma and coefficient of viscosity eta. So when this ball is falling down through this liquid or fluid, then it has certain velocity, and we have seen that eta sorry, viscous drag will be 6 pi eta rv. 6 pi eta rv, that means the viscous drag is 6 pi eta rv. 6 pi eta rv, let me just remind you that. So when the ball is falling, there are three forces acting on the ball. Three forces. What are those? We have already learnt about upthrust or buoyancy force. So one force which will be given by the liquid, so buoyancy force or upthrust, which is acting on the ball in the upward direction. Then there will be this viscous force which will be acting upward direction. So that is F over here. So two forces, one is upward thrust or buoyancy force acts on the body in the upward direction, and viscous drag also will act in the upward direction. And only the weight of the ball will or body will act in the downward direction vertically. Okay, so weight of the body will be acting downward, and other two forces like upthrust and this force is viscous drag, so those two will be acting upward direction. Okay, now as the velocity increases, see, this viscous drag increases. Okay, viscous drag increases, and that's how, see, some time will come, at some time, like at certain situation or at certain stage, what will happen, the sum of the upward forces will be exactly equal to the downward force, and when this happens, body moves with a uniform velocity. Okay, this ball will move with uniform velocity because no force is acting on that. According to by first law of Newton, we can say that a body can move or it can fall uh, with uniform velocity if there is no force acting on that body. So I am at a stage or situation where upthrust is exactly equal to the weight of the body. So at this situation, the ball will move with a uniform velocity, and that velocity is actually the maximum velocity of the ball and that particular velocity with which it moves after this thrust and viscous drag becomes equal to the weight of the body. That velocity is called terminal velocity. So terminal velocity is the maximum velocity maximum velocity attained by the object when upthrust, sum of the upthrust becomes exactly equal to the weight of the body. So that velocity is called terminal velocity, and when it is at terminal velocity, then we can write that u plus f is equal to w. W is, suppose the ball has mass m, so it will be so let us say it has a radius. It has a radius small r. Suppose small r has the radius of the ball. So and it has a density rho also. So what is the weight? Weight will be mass into g. What is mass? 4 by 3 pi small r cube. Then rho into g. Okay. And what is this force? If we know already 6 pi eta r v. Okay. And what about this u? U is the buoyancy force. You know the buoyancy force will be the weight of the displaced fluid by this ball. So displaced volume of the water, so or the fluid is by r cube, and sigma is the density, and g, this will be the upthrust. Okay, now we'll just equate all of them. Let me write it here. So 4 by 3 pi r cube sigma into g plus 6 pi eta rv is equal to, and this v is actually now terminal velocity. This is terminal velocity is equal to 4 by 3 pi r cube rho into g. Now we have to solve for terminal velocity, so v will be 4 by 3 pi r cube rho minus sigma into g divided by 6 pi eta and r. So if we simplify a bit, I'll just clean this portion so that you understand it better. Now let us simplify this calculation. 4 by, so it is okay, so 2 by 9. Okay, so pi goes off, so 2 by 9, then it is r square into sigma minus, sorry, rho minus sigma into g divided by eta. Okay, so this is what we get as terminal velocity. So what is the expression for terminal velocity and how it varies with time, we'll see here. So what is the expression for terminal velocity? That is 2 by 9 into r square rho minus sigma divided by eta into g. So this is the terminal velocity, expression for the terminal velocity. So this is the expression for the terminal velocity. You have to remember this. Sometime there will be numerical problem depending on this. Like just if you remember this terminal velocity formula, then you are done with the problem. Now see the terminal velocity, how terminal velocity or the velocity of the falling object, velocity of the falling sphere is varying with time. So this is time actually. So time versus velocity graph. See when time was zero, that means at the beginning it is actually relieved from rest. So there was no velocity, and slowly velocity goes on increasing. Velocity goes on increasing. It will grow, or yeah, it will becoming constant and maximum at certain time, and after that it doesn't change. Okay, so we are seeing that velocity increases slowly until it reaches to its maximum value, that is the terminal value. Okay, velocity increases slowly, and here it becomes constant, and it is the terminal velocity. This is the terminal velocity here onwards. This is the terminal velocity. Okay, so this is how we have to understand about Stokes law and terminal velocity, etc. We don't have further time. What we'll do, we'll stop it here for today. Next day we'll take up numerical problem depending on terminal velocity, Stokes law, etc. Okay, so we'll stop it here for today. We'll discuss this topic again on Monday next week. Okay, so bye for today. Thank you for your patience.